Hi, good day. So for today, we are going to talk about the Wilcoxon signed rank test. The Wilcoxon signed rank test is another way on how we can find the significant difference between two different sets of data or two different variables that came from dependent samples. Unlike the paired samples t-test, Wilcoxon signed rank test can only be used if the data that we have, either one of the data or both of the data that we have, are not normally distributed, and therefore, Wilcoxon signed rank test is considered a non-parametric test. Also, because in Wilcoxon signed rank test our data is not normally distributed, then the most appropriate level of measurement that we should use here is under the ordinal scale, not interval or ratio scale, but ordinal scale. Now, just like in paired samples t-test, we also have a decision rule here, and that is, if our computed Wilcoxon value is less than or equal to the critical Wilcoxon value, then we are going to end up rejecting the null hypothesis. Now, to see how Wilcoxon signed rank test works, let's have here an example research entitled The Effectiveness of STS Approach in Teaching Science. Now, for us to be able to prove how effective the STS approach in teaching science is, we obtained here 10 different students, and these 10 different students serve as our dependent samples. Now, what we did here was, we let them took two parallel 50-item tests in science. Okay? Now, the first 50-item test in science was taken before the STS approach in teaching science, and the second 50-item test was taken after the STS approach in teaching science. And for that one, we now have here the pre-test scores and post-test scores. Now, take note that these pre-test scores and post-test scores only came from the same set of samples, and that is these samples. Therefore, these samples here are considered dependent samples. Okay? Now, let's assume that one of these data, the pre-test scores or post-test scores, one of these data is not normally distributed, and therefore Wilcoxon signed rank test is the best way on how we can describe or on how we can find the significant difference between these two data. Okay, so what we are going to do here is, first, we are going to get the individual differences between the pre-test scores and post-test scores. Then, we are going to get the absolute value of those differences. And then, we are going to rank the absolute value of those differences. Now, we have here the differences in pre-test scores and post-test scores. Like, we have here -7 as the difference of 23 and 30. -3 as a difference of 37 and 40, and so on and so forth. And as you have noticed here, the only positive number that we have here is 2. Now, right after we get the differences, we are going to get or obtain the absolute value of these differences, and we will now have this new column, the absolute value of the differences. So all of the negative numbers that we have here will now turn into positive numbers. So we will have here 7, 3, 2, and so on and so forth. And after we get the absolute value of these differences, we are going to rank these values. Okay, now, in ranking, the higher the number, the higher the rank. The smaller the number, the smaller the rank. And so, as we have noticed here in our absolute value of differences, the smallest value that we have here is 2. Okay, this one. Okay, and that's why this will now be ranked first. Okay, so we will have here another column for rank. Okay, so this number 2 here will now rank first here. Okay, of course, right after number 2 is number 3, so that will now be our second in rank, 3. However, we have here 2 3s. Okay, we have here 2 3s, this one and this one. So, they will actually share the same rank. Okay, these 2 3s here will share the ranks 2 and 3. Okay, however, none of them are actually greater, or none of them is actually greater than the other. So, what we are going to do here is, just like in Spearman's law correlation, we are going to add the ranks that they actually share. So, rank 2 and 3. These 2 3s here share the same rank, ranks 2 and 3. Then, okay, and divide it by the number of data that actually share that rank, those ranks. So, these ranks 2 and 3 are actually shared by 2 3s here, and therefore we have here 2 data that actually share the same ranks. Okay, so rank 2 plus rank 3 divided by 2, so that is equal to 5 over 2, or 1.5. No, not 1.5, but 2.5. Sorry, 2.5. That's why our 3 here is actually rank 2.5 and another 3 here is actually rank 2.5. Now, because we already used up rank 3, the next number will now be rank 4. Okay, so again, yung next na number natin ay hindi na mararank as rank 3 kasi nagamit na natin siya. Okay, so yung next number natin ay pang rank 4 na kasi nagamit na natin si rank 3. So the next smallest number here is 5. This one, 5. That's why this 5 here will now be ranked 4th. Okay, and the next smallest number is 7. 7. And it will now be ranked 5th. Okay, and right after this 7 is 8, of course. And that will now be ranked 6th. Okay, and right after 8, meron ba tayong 9? Wala naman. So, right after 8, we have now 10. Diba? So, we have here 10. Okay. And that will be ranked 7th. Dapat, diba? 7th. However, we have here 10. We have here 3 10s here. This one, okay. This one, and this one share the same rank. Okay, these 3 10s here share the same rank. So, they share the ranks 7, 8, and 9. Okay, they share the ranks 7, 8, and 9. However, none of them is actually greater than the other. So what we are going to do here is, okay, to add the ranks that they actually share. So they share the same ranks, rank 7, rank 8, and rank 9, and then divide it by the number of data that actually share those ranks. So the number of data that share these ranks are actually 3. Okay, so we have here 3 10s, so that's divided by 3. So rank 7 plus rank 8 plus rank 9 is equal to 24, divided by 3 because we have here 3 10s. Okay, divided by 3, and that is equal to 8. So individually, these 10s, each 10 here will be ranked 8. So 8, 8, and 8. Okay, now because we already used up rank 9, the next value that we will have here will now be ranked 10th. Okay, pang 10 na yung next na value na irarank natin. So the next, the highest value that we have here is 13, and therefore that will now be ranked 10th, not 9th or not 8th. For the next one, let's determine the null hypothesis, the alpha level or level of significance, the sample size, the type of test, and the critical value for the Wilcoxon. Now, for the null hypothesis, our null hypothesis here is there is no significant difference between the pretest scores and post-test scores, or the pretest scores is just equal to the post-test scores. For the alpha level, again, our alpha level will always be 0.05 or 5%. Our sample size here is 10. We have here 10 samples. Okay. And our type of test here is two-tailed. Okay, why two-tailed? Because we didn't use any comparative adjectives or any direction in our null hypothesis. We did not say pretest scores will be greater than the post-test scores, or pretest scores will be lower than the post-test scores, and so on and so forth. We don't have any direction here. That's why our test here is two-tailed. Okay, now for the critical value for the Wilcoxon, there are actually 3 things that are actually important for us to be able to determine this critical value in Wilcoxon: the alpha level, the type of test, and our sample size. And since we already determined these 3, the alpha level, the sample size, and the type of test that we have, let's now go to the Wilcoxon value, or the Wilcoxon critical value table, to check what will be our critical value for the Wilcoxon. This is our critical value table for Wilcoxon signed rank test. Here, we know that our type of test is two-tailed, our alpha level is 0.05, and our sample size is 10. By intersecting the value under 0.05 in two-tailed test and the value under 10 as our sample size, then we can say that our critical value, or W-crit, is 8. After checking the critical value table for Wilcoxon, we now know that our critical value for Wilcoxon is 8. Therefore, if we are going to go back on our decision rule earlier, if WCOM, or the computed Wilcoxon, is less than or equal to 8, which is actually our critical value for Wilcoxon here, then we are going to reject the null hypothesis. Now, for us to be able to determine our computed Wilcoxon, there are actually 2 things that we need to sum up in our table. Okay. Number one, we need to sum up all the ranks that are associated to positive differences. And second, we need to add or to sum up all the ranks that are actually associated to negative differences. In this case, the only positive difference that we have here is 2. Okay, and therefore, these 2 here will now serve as our positive rank, and this 2 here is actually ranked first, and therefore, we have here t positive is equal to 1. That is actually the only positive number that we have in our difference, and its rank is actually 1. Okay? Now, the second thing, again, is we need to sum up all the ranks that are associated to negative differences. In this case, our negative differences are -7, -3, -10, and so on and so forth. And we need to sum up all their ranks. So, their ranks are 5, 2.5, 8, and so on and so forth. Okay, so 2.5 plus 2.5 plus 4 plus 5 plus 6 plus 8, 8, 8, and 10. These are actually the ranks associated to negative differences. Okay, and so if we are going to add these ranks that are associated to negative differences, then we will have here 54. Okay, now what will be our computed Wilcoxon here? Our computed Wilcoxon here will be the smallest among the two. Okay, now we have here two values, 1 and 54. Which one is smallest? Obviously, the smallest one is 1, and therefore, our computed Wilcoxon is 1. Now, let's have the analysis. For the analysis, okay, since WCOM, okay, our computed Wilcoxon is 1, okay, is less than the WCRIT, our critical Wilcoxon value is 8, okay. So, since 1 is less than 8, then we are going to end up rejecting the null hypothesis. Therefore, what will be now our conclusion here? Since our null hypothesis is that pretest scores are just the same as post-test scores, or there's no difference between pretest scores and post-test scores, then we are going to reject this, and our conclusion will be the pretest scores is not equal to post-test scores, or there is a significant difference between the pretest scores and post-test scores. That is how we can use the Wilcoxon signed rank test in determining the significant difference between two different data from dependent samples that are actually not normally distributed. So thank you for listening and good day.